Dear students, today we are going to discuss about lag lead compensator. In the previous video, we have discussed about lag compensator and lead compensator. Now, lag lead compensator is a combination of both lag compensator and lead compensator. And in the circuit case, we are not using lag compensator and lead compensator with separate circuit. We are using, instead of that, we are using lag lead compensator. Okay. So, a compensator having the characteristics of lag lead network is called lag lead compensator. In the case of a lead compensator, it increases the bandwidth and speeds up the response and decreases the maximum overshoot in the step response. Whereas lag compensation increases the low frequency gain and thus improves the steady state accuracy of the system. So whenever we want this type of qualities, we use lag lead compensator instead of using both the lag compensator and the lead compensator, because it is economical to use the lag lead compensator rather than introducing both these compensators separately. Okay. So first of all, go to the S-plane representation of the lag lead compensator. We have gone through the S-plane representation of lag compensator and lead compensator. So here the lag lead compensator S-plane representation consists of both the S-plane representation of lag compensator and lead compensator. You can see here that this poles and zeros represents the lag section, whereas this poles and zero represents the lead section. So a lag section has one real pole and one real zero, and in that case pole will be at the right of the zero. And in the case of lead section, it also has one pole and one zero, and in this case pole will be left to the zero or zero will be right to the pole. That is the case, and this represents the pole zero plot of the lag lead compensator, and it is represented in the S-plane. S-plane means there will be real axis and imaginary axis. So next we can go to the transfer function of the lag lead compensator. So it is represented by Gz of S, and it is a product of the transfer function of the lag compensator section and lead compensator section, and its equation is S plus 1 by T1 divided by S plus 1 by beta T1, that represents the lag section, and that will be multiplied by S plus 1 by T2 divided by S plus 1 by alpha T2. This represents the lead section, and here beta is greater than 1 and alpha is in between 1 and 0, 0 and 1. So the realization of the lag lead compensator using electrical network is shown in the figure, and this section represents the lag section and this represents the lead section. That is, it is a series combination of RC network, and here it is represented by the parallel combination of R and 1 by SC1. Here 1 by SC1 means it is the S-plane representation, S-domain representation of the capacitor. Now let us go to the procedure for designing of the lag lead compensator using the bodeplot, and it is a university question. That means what is the procedure for designing steps for lag lead compensator? That is one of the university question, KT university question, and the design procedure contains 11 steps. Let us go to the steps. It is similar to the steps that we have studied in the case of lag compensator and for the case of lead compensator. So here first we will discuss about the lag compensator design steps, and then we will go directly to the lead compensator design section. Okay, and then we will draw the block diagram of the lag lead compensator. Okay, so first step is, so we will be given in the question, we will be given by a transfer function. In that k will be unknown, that means gain will be unknown. So we have to first determine the open loop gain k of the uncompensated system, and that should satisfy the specified error requirement. That is the first step. And in the second step, next we have to draw the bodeplot of the corresponding to the gain. That means a bodeplot corresponding to the uncompensated system gain. And after plotting the bodeplot, we can determine the phase margin. For that, we have to go to the phase plot where we can determine the gain crossover frequency. See, when we are going to the board plot, we will have two plots, magnitude plot and phase plot. In the magnitude plot, where the magnitude graph crosses the 0 dB, that will give you the gain crossover frequency, and corresponding to that gain crossover frequency there will be a phase, and that phase is 5GC. Okay, that means 5GC is the phase of the magnitude plot at a gain crossover frequency. From that phase we can determine gamma. Gamma is phase margin. So gamma will be equal to 180 degree plus 5GC. So if the gain margin is not satisfactory, then compensation is not required. So these quantities we will obtain from the graph itself. So once we obtain the value of gamma, then we can check for whether that gamma value satisfies our requirement. If it is not satisfied, then we have to design a lag lead compensator. So for that we can go for step 4, where we have to choose a new phase margin. So these steps will be, first of all, we have to write the equation gamma n equal to gamma d plus epsilon, where epsilon we are choosing the value as 5 degree. See, you have gone through the same steps in the case of lag compensator and lead compensator. In that case also we have choose the value of epsilon is equal to 5 degree. So the design steps are similar. Okay, there will be no confusion for designing. Okay, so next we can find the value of gamma n by using that equation. So once we obtain that gamma n value, we will get a corresponding gain crossover frequency from the phase plot or phase plot graph from the board plot. So that new gain crossover frequency is represented by omega GCN, and corresponding to that omega GCN there will be 5 GCN, and that represents the phase of the G of j omega. Once you obtain this 5 GCN, you can find gamma n is equal to 180 degree plus 5 GCN. So 5 GCN will be equal to gamma n minus 180 degree. That is your equation. These steps are similar to the previous lag compensator steps and lead compensator section. So go through that videos also. Then you will easily you will easily get the idea. Okay. So once you get the gamma n value, once you get the 5 GCN value is equal to gamma n minus 180 degree, you can just mark that omega GCN in the graph also. So from that value, you will get a particular value for omega GCN. So next step is you have to choose a new gain crossover frequency of lag compensator that should be greater than omega GCN. That means you will select a value omega GCL that will be greater than omega GCN. So that is the difference here. So in the step 5, we will go for a new value of omega GCL which should be greater than omega GCN. So that is the only difference from the previous videos. So next step is step 6, and in that step we will calculate the value of beta. We have the equation for beta as AGCL will be equal to 20 log beta, where AGCL equal to magnitude of G of j omega. See, that value will be obtained from the graph. See, we have chosen a value of omega GCL. Corresponding to that omega GCL, there will be a particular gain that will be obtained from the board plot, and that gain value will be equal to AGCL. So AGCL has an equation that will be equal to 20 log beta. From that equation we will get beta value. So beta will be equal to 10 raised to AGCL by 20. So now you got the value of beta, and next we can determine the transfer function of the lag section, and for that we know that the transfer function will be having the equation G1 of S is equal to S plus 1 by T1 divided by S plus 1 by beta T1. So here beta is obtained. Next we have to calculate the value of T1. So we know that lag compensator introduces a 0 and also a pole. So 0 of the lag compensator is given by ZC1 equal to 1 by T1, that will be equal to omega GCL by 10. So here you should note the value. Here we are using omega GCL to find the value of T1. Okay. So T1 will be equal to 10 by omega GCL. So we will obtain T1 value. Next we have to determine the pole of the lag compensator. That pole will be equal to PC1. That will be equal to 1 by beta T1. So by using these values we can find out the transfer function g1 of s is equal to beta into 1 plus st1 by 1 plus s beta into t1. So this is the steps. So here only the difference for designing the lag section is here we are choosing a value omega GCL, and by using that omega GCL we are calculating 0 and poles of the lag compensator. That is the only difference here. Other equations are same. Okay. Also here we are calculating beta by using the value AGCL. Okay. So that is the difference. So you should note down that. And next, once we obtain the transfer function for the lag section, next we can go to the designing of the transfer function of lead section. And you know, the lead section has got a transfer function alpha equal to alpha into 1 plus st2 by 1 plus s into alpha into t2. So you have to find out the value of alpha, and next you have to find the value of t2. So here alpha has an equation alpha equal to 1 by beta. So from the border plot, we have to choose a value of omega m, which is the frequency at which the gain is minus 20 log 1 by root alpha. That you should note down. That is, we have to find the value of omega m, and that omega m is the frequency corresponding to the gain minus 20 log 1 by root alpha. So first you calculate alpha from the value of beta, and next you have to calculate the gain by using the equation minus 20 log 1 by root alpha, and correspondingly you have to find a value of frequency omega m. Once you obtain the value of omega m from the dot plot, you can easily find out T2 by using the equation T2 equal to 1 by omega m into root alpha. So you have the values T2 and alpha now. So you can find the transfer function G2 of S is equal to alpha into 1 plus S T2 by 1 plus S alpha T2. So that is the transfer function of the lead section. So it is easy. So next we can combine these transfer functions to get the overall transfer function of the lag lead compensator. So overall transfer function of the lag lead compensator GC of S is equal to G1 of S into G2 of S. So you can direct multiply these two quantities, and here you know alpha equal to 1 by beta. So GC of S, that is transfer function of the lag lead compensator, is equal to 1 plus ST1 into 1 plus ST2 divided by 1 plus S beta T1 into 1 plus S alpha T2. So we can show this in a block diagram as like this. See, this was the original transfer function gain, open loop gain. So you are connecting this GC of S in series to this G of S, and there will be a feedback path. So this is a representation or block diagram representation of the lag lead compensator section. And here the open loop transfer function of the compensator system will be obtained by multiplying these two quantities. That is equal to 1 plus ST1 into 1 plus ST2 into G of S divided by 1 plus S beta T1 into 1 plus S alpha T2. So next, in the 11th step, you can draw the dot plot of the compensator system and verify. So here also you have to verify the result and verify whether the specifications are satisfied or not. Suppose the specifications are not satisfied, then we have to choose another choice of alpha such that alpha less than 1 by beta, and repeat the steps 8 to 11. That is the important thing. Once you obtain this value, you have to draw the dot plot of this compensator system and verify the specifications are met or not. If it is not met, then you have to choose another value of alpha. By choosing another value of alpha, and you have to that means alpha here is alpha equal to 1 by beta. So you have to choose alpha such that alpha should be less than 1 by beta, and you have to then repeat the steps 8 to 11. That is the thing. Okay. That's all about this lag lead compensator, and it is a KTU university examination question. And go through the procedure and prepare notes. Okay. Thank you.